Hey class, today we're going to be talking about thermochemistry. This is our first lesson in this chapter, and we're going to focus on the nature of energy. So let's start with an introduction. So in this chapter, we will begin to explore energy and its changes. And there are two terms you might hear. The first is thermodynamics. This is the study of energy and its transformation. So how is mechanical energy transformed to chemical energy, etc. The next one is thermochemistry. This is the title of this chapter. It is defined as the relationship between chemical reactions and energy changes that involve heat. Hence the name thermo. There are examples where thermochemistry is used all around you in your everyday life. These examples include the combustion of gasoline when you drive your car, the production of electricity using the natural resource of coal, heating homes using natural gas, or even the batteries being used to power your electronic devices. So, what exactly is energy? Energy is defined as the capacity of doing work or supplying heat. So, work and heat are going to be talked about quite a bit in this chapter. Now, ways that energy and matter are different is one thing you have to take into account is energy does not have mass or volume. So how exactly are we able to measure it? How do we know that it's there? Well, the way that we detect energy is by detecting the effects it has on other objects. For example, when objects heat up or objects move based on work being done. Now, there are different units that we use for energy, but the SI unit for energy is known as the joule, which is abbreviated with a capital J. Now, 1 joule equals 1 kilogram times meter squared divided by second squared. Please note that my mass right here is in kilograms. Now, because a joule is a small amount of energy, we are going to be using prefixes as well, and one of the common prefixes that we use is kilo. So a kilojoule is abbreviated lowercase k, capital J. One thing to note in your notes is that there are 1,000 joules in 1 kilojoule. Besides the joule, there are other units out there that we use, and one that we use in our everyday life is a calorie. We think of calories when we're counting food because food gives us energy. Now, the calorie is equal to 4.184 joules. I want you to pay attention to this capitalization right here. A lowercase calorie is not the calorie you think of when you're eating food. A calorie in nutrition is actually called a kilocal, or we denote the difference by giving it a capital. So remember, a capital C is the same thing as a kilocal. And note there are 1,000 calories in 1 kilocal. So let's do some conversions now that we've talked about these different ones on the previous slide. Here we have, it says, convert 200 calories, also known as a kilocal, into joules. So let's start our conversion with what we know. So I'm going to put kilocal because it helps me be able to differentiate between calorie and then a big case calorie. So here I have kilocal, so I'm going to put kilocal on bottom. And I want to get to joule, but there is no conversion between kilocal and joule. So you can actually go to a regular calorie first. Now remember, there are 1,000 calories in 1 kilocal. From there, I can actually cancel out calories and put joule on top. Remember, our conversion on the previous slide was 4.184 for every 1 calorie. And now notice that my units are canceling. And I can actually go ahead and take 200 times 1,000 times 4.184. And you get your answer. Here I have 4 sig figs, so I'm going to make sure my answer has 4 sig figs. Moving on to the next problem. Here it says convert 350 joules to calories, and notice my calories is a lowercase c. So I'm going to start with this 350 joules, And I want to get rid of my joules, so I'm going to put it on the bottom. And we have a conversion between joules and calories. So for every 1 calorie, there are 4.184 joules. We can actually equal that out because we want lowercase calories, and you get 83.652000765. I want 2 sig figs because this 0 at the end does not count. There's not a decimal. So I get about 84 little calories. On the next example, you guys can try to pause this video and work it out yourself, but we're going to go through the answers as soon as you unpause. Okay. So hopefully you guys have tried to work this out yourself, but here we're going to go ahead and write down what we get. Here we have 250 calories. Notice it is lowercase. And we want to convert it to joules, so we're going to use our conversion that we know. We're going to put calorie on the bottom so it cancels. 4.184 joules on top because that's what we want. And we actually get about 1046 joules. One thing that you're going to notice is that here we only need 2 sig figs, but I can't just say one. I can't put a decimal anywhere. I can't change these to zeros and have 1 sig fig. The best way to put this to have the correct number of sig figs is put it in scientific notation. So 1.0 times 10 to the third joules. And the last one, hopefully you guys tried this one as well. Here we're going to start with what we're given. And here notice we're going to go to a kilocal. So in order to go to kilocal, the easiest thing to do is change my joules to lowercase cals first. From there, I can go from calorie to a kilocal or capital calorie. Remember, there are 1,001. When you guys go to find this, you get the answer 2.5. Now we need 4 sig figs here. So if you put 2.5, we need to put 2 more numbers that would count. So 0, 0 would give me the proper number of sig figs. From there, we can actually classify energy. There are 2 types that we're going to learn about. The first is potential energy, and the second is kinetic. Potential energy is the energy stored in bonds between atoms, hence the chemical bonds, and this can actually be released during chemical reactions. We can release heat. The other one is kinetic energy, and this is energy that an object has when it's in motion. And remember, all particles of matter are in motion. So kinetic energy takes many forms. There is thermokinetic energy, there is radiant, electrical, sound. We're going to focus a lot on the thermal and chemistry part of it. The magnitude of kinetic energy, which is abbreviated E with a little k to mean kinetic, is going to depend on the mass and the speed of an object. This is our formula for kinetic energy, and you're going to be using it. It's 1/2 mass times velocity squared. And one thing I want you to know about this mass has to be in kilograms based on the unit. Since our unit is joule, notice that the unit is kilograms. So our mass needs to be in kilograms. And our velocity is going to be equal to meters per second. Again, I stated it down here, mass in kilograms, and your speed needs to be in meters per second. Here we're going to do 2 example problems. It says the kinetic energy of a 0.0306 kilogram golf ball is traveling 64 meters per second, and I want to know what its kinetic energy is going to be. So when we look at this, we have to make sure that we're setting it upright. Remember, kinetic energy equals 1/2 mass times velocity squared. So we have 1/2. My mass is already in the correct units, so I don't have to change it. 0.0306. My velocity is already in the correct unit, so I can plug in 64 and square it. Make sure you do your orders of operations first. You want to square the 64 and then you guys can multiply across. Or you can plug it into your calculator in one foul go and you get approximately 62.6684. Now here this one has 3 sig figs, this one has 3 sig figs, so my answer 62.7 should have 3 sig figs as well. Now what if you are given a problem but instead of finding kinetic energy you have to find something different such as velocity? Here it says, what is the velocity? At what velocity must a 96.1 kilogram jogger travel to have the kinetic energy of 1,054 joules? So here we already have my kinetic energy. So we're going to plug that in for my kinetic energy. Equals 1/2. I have my mass. Note, it's in the correct unit. My velocity, I don't know, so I'm going to put x, and that's going to get squared. The easiest thing to do is to combine your 1/2 and 96.1 first. And that's going to equal 48.05. And then I'm multiplying here by x squared. I'm then going to divide by that 48.05 to get it x closer to being by itself. And you actually get 21.9354837 equals x squared. In order to get x squared by itself, we're going to square root it. So x is about 4.683533. Here we have 4 sig figs here, but 3 here. So my answer is only going to go to 3 sig figs, 4.68. And here I'm asking for velocity, so meters per second. So in case you're wondering, velocity is just speed plus direction. So it's a type of speed. Here is a problem. This is one I want you to try to pause the video and see if you guys can get it yourself. One thing to know is the atomic mass of argon is what you're going to use for the mass. So let's go ahead and work through this problem. Hopefully you've worked through it, you paused it, and now let's see if you got the right answer. It says, what is the kinetic energy of an argon atom moving at a speed of 650 meters per second? Hint, you need to use the atomic mass of argon. So one thing you should know is we don't know my kinetic energy, so I'm going to put x equals 1/2. Now I asked you guys to use the atomic mass of argon. The atomic mass of argon is 39.948. Now remember, this is grams per mole, so I have my unit in grams. I need to change this to kilograms. So you can actually divide by 1,000 to get it into kilograms. So when you get it into kilograms, you get 0.039948 kilograms of argon. And then here we're going to multiply it by our velocity, which is already in the correct units. And then we're going to square that. Again, you can square this first and then multiply, or you can put this in your calculator altogether. But you should get 8,439.015. Unfortunately, I can only have 2 sig figs based on my speed. And the best way to get 2 sig figs here is either to round it to 84,000 joules, or you can put it into scientific notation and put 8.4 times 10 to the third joules. Either one of these are acceptable answers. Okay. Now, remember, we're going to talk about a few more things in terms of energy. We define energy as the capacity of doing work or supplying heat. So let's actually talk about those two definitions. Work, which is abbreviated W, is the energy transferred or used when a force moves an object. So let's say an object. And when I say force, it's a push or a pull. So work's defined as force times distance. Again, force is any push or pull on an object, and we found force in the last chapter. It is mass times acceleration due to gravity. Remember, for our force, our mass was in kilograms, and our acceleration due to gravity was 9.8 meters per second squared, and our unit for force was Newton. Heat, which is abbreviated by the letter Q, is defined as the energy that transfers from one object to another because of a temperature difference between those two objects. One thing to know about temperature and heat is it's going to be transferred from a hotter object to a colder object. So that's why when we touch something hot, it's because that stove is hotter than us, so the heat comes into our hand. The reason we feel objects as cold is because we are hotter than an ice cube, so actually heat is leaving our hand, so that's why we feel chilly. One thing to know is that heat is not the same as temperature, and you will notice this quickly when we talk about SI units. SI unit for heat is joule, but if we look at temperature, it is Kelvin. The other thing comes into the terms of its definition. Heat of an object is the total energy of all the molecules inside it, but temperature's definition is a little bit different. This is actually going to be the average heat, so not all of it. I like this little image because it does show all the comparisons between the terms heat and the term of temperature. And that's the end of today's lesson. If you have any questions, please make sure that you ask. And otherwise I hope you guys have a great day.